SwayamPrabha. Digital India. Educated India.
In this lecture, we are going to start our discussions on central force motion. Now, the first question that arises is, what is central force motion? Central force motion is the motion of a massive particle moving in a central force field. Now, the question is, what is a central force field? Central force field is a force field in which if you place a particle, the force that acts on the particle is towards a fixed point in the inertial space. Such a force field is called a central force field. You can realize central force fields in various ways. This is one example. You have a pivot and you have a spring to which a mass particle is attached. Now, this spring is going to give you a central force field. You take the mass to any point, the force that acts on the mass will always be directed towards this pivot anywhere. So, the force will always be directed towards the pivot center. This is a central force field, but in this lecture we are not going to discuss these kinds of central force fields. Here we are going to discuss gravitational central force field generated by a gravitating mass, which will be assumed to be fixed. What happens if it is not fixed? We are going to discuss, we are going to see that. So, the overview of this lecture is as follows. Since this is going to be gravitational central force field, which has relevance to planetary motion, therefore, we are going to start with Kepler's laws of planetary motion. Then we are going to look at Newton's law of gravitation, and then we are going to study the dynamics of a particle in a central gravitational force field. So, central force motion, as I mentioned, motion of a particle under the influence of a fixed central gravitating body. So, central gravitating body is considered, and that is considered to be fixed. Now, all this started with Tycho Brahe. People might have observed many things before, but Tycho Brahe, who was a Danish nobleman and a wealthy one, and had various hobbies or he had varied interests, and one of his interests was collecting astronomical data. He had his own observatory, and his data was very accurate. Therefore, he had this compilation of very accurate astronomical data, mostly motion of planets and natural satellites possibly. Johannes Kepler was assistant of Tycho Brahe. Now, all this data were collected by Tycho Brahe himself. Now, he did not very easily share with Johannes Kepler this data, but after Tycho Brahe's death in 1601, Johannes Kepler being his assistant, he inherited this data, and from these very accurate observations of Brahe, he observed Kepler observed some regularities in the motion of planets. which he could formulate as his 3 laws. But remember that these laws were as observed from nature and they are purely kinematic. If you will go through the laws, as you will see very soon, that these laws only said, for example, what kind of path a particle will take or a planet will take around the sun, or maybe the moon will take around the earth. These kinds of things. I mean, it was not so, and these were completely based on the observations that Tycho Brahe made. Then came the master. He gave the universal law of gravitation in one stroke. Using his laws and this universal law of gravitation could generate, I mean, you can now solve these equations and see how a massive particle will move, a planet will move around a central gravitating object like a sun, like the sun. Therefore, now it came into the realm of kinetics and you can do calculations and possibly you can also predict paths which are not normally observable, like hyperbolic or parabolic paths. They are very difficult to observe. Now, that can be done from Newton's laws of motion and this Newton's law of gravitation. So, you can generalize trajectories, now you can study dynamics of satellites, etc. But Kepler's laws were purely based on observation and it tells us about path and time taken, etc., which are observational facts. But this is very interesting that he could find these regularity in the data of Tycho Brahe. Now, Kepler's laws of planetary motion, the first law says that every planet moves in an elliptic path with sun as one of the foci. Now, ellipse has 2 foci and when a planet moves around the sun is at one of the foci. The second law of Kepler states that the sun planet line segment, sweeps out equal areas in equal times, purely kinematic and observational. The ratio of square of the orbital time period and the cube of the semi major axis of the elliptic path is same for all planets. These are kinds of regularity. I mean, to find this regularity from find from all the data that Tycho Brahe had taken or observed or noted down is in itself a huge task, and which Kepler did. Then comes Newton's law of gravitation, which puts all these, I mean, the study of motion of planets as a part of dynamical calculation, dynamics. Imagine 2 particles, one is mass m1, the other is of mass m2, separated by a distance I have shown as a vector r. Then what Newton's universal law of gravitation states is that the magnitude of the force is equal to the universal constant, gravitational constant G, capital G, m1 m2 by r square, where r is the magnitude of the distance separating the 2 particles. As a vector, the force on body m2 can be represented as minus g m1 m2 by r square times r cap. R cap is the unit vector in the direction of r vector. I have shown, you will notice that I have shown r with a certain direction. This r vector, the direction is from m1 to m2. Therefore, this force vector on m2 is in the direction of minus r cap. and this can be written as this form, which is also very useful form, minus g m1 m2 by r cube. What I have done is multiply this by r and multiply this by r, and so r is the magnitude of the distance. So, denominator becomes r cube, numerator r cap into magnitude is nothing but r vector. And this is exactly equal and opposite to the force on particle 1, which follows from Newton's third law. Capital G is the universal gravitational constant, which has this value of approximately 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. This is experimentally determined. M1 and M2 are also called gravitational mass. We have been using in Newton's law mass m, mass into acceleration is force. That mass is usually referred to as the inertial mass. For example, m into acceleration, mass into acceleration is the inertial force. So, that mass that comes in Newton's laws of motion, Newton's second law of motion, is the inertial mass, and the mass that comes here in the gravitational law of Newton is called the gravitational mass. Now, there is no reason why these two should be equal, but they are found to be equal to a very high level of precision. R is the separation distance. Now, you can make some simplifying calculations. For example, weight of a particle on the surface of the earth. So, mass of that particle is small m, and acceleration due to gravity on the surface of the earth is g e, and that must be equal to, from the gravitational law of Newton, g mass of earth times mass of the particle by radius of the earth square, because on the surface of the earth roughly the particle is at the radius, the separation distance is the radius. From here you can get the acceleration due to gravity on the surface of the earth times radius of the earth square is equals to capital G into mass of earth. Sometimes we will replace this capital G into m e by acceleration due to gravity times radius of the earth square. Okay, now we will come to the central force motion, in which the dynamics of a movable point particle of mass small m in the gravitational field of a fixed particle of mass capital M. Till now what we were discussing was the force, gravitational force between two particles. Now I fix one of the particles, and the force that is generated, the force field that is generated is governed by that capital M, which has been fixed, and the small m is moving. We want to study the dynamics of that small m. Capital M we have fixed. Now, this simplification, now this as a problem, I can always say that I fix in inertial space, I fix a large mass capital M and I study the dynamics. But for this study to be relevant to planetary dynamics, we have to make this assumption that small m by capital M, which is the gravitating mass, the primary gravitating mass, the small m by capital M is much less than 1. Then we can assume that the central mass, the gravitating mass capital M, is roughly fixed, can be considered to be roughly fixed. We will see what happens if it is not, but that in a later lecture. How much is this condition satisfied? Let us look for the Sun Earth system. Mass of Earth, if I think that I want to study the dynamics or the motion of Earth around the Sun, then I must take Earth as small m and the gravitating mass as the mass of the Sun, and that turns out to be, this ratio turns out to be 3 into 10 to the power minus 6. which is small enough, and therefore, sun is roughly a fixed body, fixed central gravitating body, and earth is a like a particle moving in the gravitational field of the sun. Mass of Jupiter by mass sun. So, if I want to study the motion of Jupiter, then with sun as fixed, then let us see what is the ratio. Mass of Jupiter by mass of sun is 9.5 into 10 to the power minus 4, roughly 10 to the power minus 3, which is not very good, but not very bad either, depends on how much accuracy you want, how long you want to study the orbit, because it is going to induce errors in the orbital motion of Jupiter. 9.5 into 10 to the power minus 4 is not a very small quantity in that sense, but still it is small. So, we might study the motion of Jupiter around the sun by considering that sun is fixed, but it will induce error, much more error than what will happen with the earth. Now, the moon and the earth. Moon is also moving around the earth, and it is being gravitated by earth as the central gravitating field. Now, this turns out to be 1.2 10 to the minus 2, which is very high. Therefore, the moon earth system, if you want to study earth as a fixed central gravitating object, then this is going to be quite erroneous. If you take the International Space Station is the largest man-made structure orbiting the earth. Mass of the International Space Station by mass of earth is 10 to the power minus 19, 7 into 10 to the power minus 19, which is quite small. Therefore, I can study the trajectory of the International Space Station with earth as a fixed central gravitating object. Now, let us look at the formulation. The acceleration of a particle in a plane. I am using the polar coordinate system, considering that this particle will be moving in one plane. Whenever there is a central fixed object, gravitating object, and a body is moving around it in the central force field, gravitational force field, this motion of the moving object will always be in a plane. These are treated as particles. Remember, these are treated as particles, and there is no other influence of other planets or other particles in the neighborhood. In that case, this motion of the moving particle will be on a plane. This plane is called the ecliptic plane, or simply ecliptic. So, earth has this ecliptic or ecliptic plane, which has the earth, sun, and the total path of earth around the sun. Everything is on that ecliptic plane. Moon around the earth also has such a plane, but that plane is slightly inclined with the main ecliptic that has sun and earth in it. So, on this ecliptic plane, we are using the polar coordinate system, and acceleration of small m, which is earth, to be considered as earth small m, let me say small m only, is given by the acceleration expression, which we have discussed so many times. Now, equation of motion is Newton's second law. Mass times acceleration is equals to the net force. I have shown the free body diagram of the particle m. So, mass times acceleration of particle m is equal to force is minus g m m by r square E r cap. Now, if you look at the two components, the first component, which is the E r component, E r cap component, and this is the E theta cap component. The E r cap component gives us mass into r double dot minus r theta dot square is minus g m m by r square. In E theta cap direction, there is no force, therefore, I have mass times the acceleration in E theta direction as 0. Now, interestingly, the second equation can be recast in this form 1 over r d dt of m r square theta dot. You can check by taking differentiation using the product rule, you will get the equation on the left. Now, what this tells us, r is not equal to infinity, r, this small r is not equal to infinity, we will consider that it is at a finite distance. Therefore, it must be true that d dt of the bracketed quantity is 0. In other words, the bracketed quantity must be a constant. And what is this constant? This constant is angular momentum. How this is angular momentum? This is r, which is the moment arm, times m r theta dot. What is r theta dot? R theta dot is the tangential velocity. Is the tangential velocity. This is r theta dot, and if you look at velocity expression in polar coordinates, and if you calculate r cross m v, r cross m v, this is nothing but r e r cap cross m times velocity vector, which is r dot e r cap plus r theta dot e theta cap. E r cap cross e r cap is 0, e r cap cross e theta cap is E z cap. If you remember, then this becomes r m r theta dot E z cap. Therefore, this is m r square theta dot, which we have. Now, let us look at, so this is angular momentum. Now, let us look at this picture. This picture is in the ecliptic plane. If I want to find the area, express this area when this line segment from the central point, central gravitating mass to the or the force center to the particle, this rotates by an angle d theta. What is the area swept? The area swept can be found out at this infinitesimal area swept is half the radius times r d theta. So, this is r d theta. Half radius times r d theta is the area of this triangle, and for d theta means it is infinitesimal change in angle. Therefore, the area of this triangle, roughly triangle which is swept by this line segment, is half r square d theta. Therefore, d a dt, so 2 times d a dt must be r square theta dot. 2 times d a dt must be r square theta dot, and r square theta dot, m r square theta dot is a constant, m is definitely a constant, but r is not, theta dot is not, but r square theta dot happens to be a constant from angular momentum conservation. Why angular momentum is conserved? Because there is no moment of any force acting about the force center. Okay. Then r square theta dot is a constant, though r is not a constant, theta dot is not a constant. So, 2 times the rate of change of area is a constant. Now, radial line therefore sweeps equal area in equal time. This was Kepler's second law. Now, this is irrespective of whether the trajectory is open or closed. Now, we come back to the equation of motion. So, this is m. So, this was the other equation, the first equation, the E r cap equation, m r double dot minus r theta dot square is minus g m m by r square, and we have this condition that r square theta dot is the angular momentum by mass, which I write as small h, which is a constant. Now, if r square theta dot is a constant, so theta dot can be represented in terms of r as small h by r square, which I can substitute in the governing equation. I can substitute this here and get an equation which is completely in terms of r. This is completely in terms of r double dot minus h square, h is a constant, remember, angular momentum by mass, h square by r cube is equal to minus g m by r square. I have cancelled m from both sides. So, this is our governing equation for r. If I can solve this equation, then I can use this to solve for theta. Suppose I can solve the r equation, then this equation I can use to solve theta. Now, this appears to be very highly nonlinear, r double dot, and there is 1 by r cube, there is 1 by r square on the right hand side, etc. But it so happens that this equation can be transformed in a very simple form. Let us look at that transformation. Define r as 1 over u, u is a new variable I am using, then r dot. So, r is a function of time, so u will always obviously be function of time, is a new variable. So, r dot is minus 1 by u square du dt, which I write as du d theta dt. This is an important step. This is an important step. Du dt I write as du d theta dt. Now, theta dot is h over r square, theta dot is h over r square, therefore, I get minus h over r square into u square, and u prime is du d theta. I write du d theta as u prime. Therefore, I get r dot as minus h u prime. Why? Because u square r square is 1, you can check, r is 1 over u, therefore, r into u is 1. Therefore, r dot is minus h, which is a constant, into u prime. So, r dot is equal to minus h, a constant, into u prime. This I can continue to find out r double dot, and that turns out to be, by simple algebraic steps, as minus h square u double prime. So, double prime means twice derivative with respect to theta, the second derivative with respect to theta of u. So, that is the expression of r double dot. Now, substitute everything in the equation of motion. You substitute everything in the equation of motion, substitute this r double dot here into the equation of motion, and you will obtain, upon simplification, you will find that upon simplification you will get this very simple differential equation, ordinary differential equation, but now the time derivatives have been replaced by derivatives with respect to theta. u double prime, this is second derivative with respect to theta, plus u is equal to g m by h square. Right hand side is completely a constant. The left hand side is a linear ordinary differential operator. Therefore, this complete differential equation is now a second order linear ordinary differential equation with a constant right hand side. Now, we will start by analyzing this differential equation. This is a second order ordinary differential equation, linear, and we are going to solve this differential equation and look at its solutions and try to characterize them. Now, the general solution of such a differential equation can be written as some constant. This is what I have written, some constant c times cosine theta plus delta. Theta is our independent variable, delta is a phase. This is typical of the solution of a second order linear ordinary differential equation, and this is a constant inhomogeneous term which comes in the solution as it is. Here, as I mentioned, c and delta, the amplitude and phase, these are constants of integration. At theta equal to 0, we will consider r as r min. You remember that u is 1 over r. We have solved the differential equation in u, and u is 1 over r, the radial coordinate. Now, we are going to set the phase delta by fixing this, that at theta equal to 0, we would demand that r is r min. That means, it is the closest approach of the particle to the gravitating central mass. This simplifies the solution form. Why? Because delta becomes 0. With this simplification, with this setting of the initial phase r equal to r min at theta equal to 0 sets the phase delta as 0. Therefore, our solution now becomes quite simple. 1 over r is c cosine theta plus g m by h square. Let us look at this figure where I have shown the gravitating central mass. This is the moving mass. E r cap and E theta cap are the coordinate axis, and at this point, if the velocity is v, velocity of the particle is v, and it makes an angle phi with E theta, then the tangential velocity magnitude, that means it is the projection of v along E theta. So, the tangential velocity v t is r v sin phi. So, this will become this will be r so v cos phi. So, this is v cos phi. So, tangential velocity v t is v cos phi. So, this is v t, and from here I can calculate h. I can calculate h. Remember, h is r square theta dot, and this is equal to r into r theta dot is the tangential velocity v t. Therefore, h is equal to r v cos phi. So, please note this, v t is the velocity cos phi, h is r square theta dot, and r theta dot is the tangential velocity v t. Therefore, h is equal to r v cos phi. So, here I have written that h is so this has to be corrected. This is v cos phi, h is r square theta dot, which is equals to r times v t. V t is r theta dot, which is the tangential velocity, which is v cosine phi. If this is the v is the magnitude of the velocity vector, then that projected on E theta cap will give you v t, the tangential velocity. Now, we have this solution form. Let us now go to geometry. It is known from geometry of conic sections. So, what are conic sections? These are essentially locus of a point whose ratio from a fixed point and a fixed line is a constant. That fixed line is called directrix, shown here in the figure, and that fixed point is called the focus, also shown here, and the radial coordinate is r, and the distance of this point red dot from the line is d minus r cosine theta, where theta is marked. So, we are using the polar coordinates, r is the radial coordinate and theta is the angular coordinate. Now, it is known that this ratio r, the distance from a fixed point and a fixed line. So, r is the distance from the focus, d minus r cos theta is the distance from the directrix. This is a constant, this is called eccentricity E. This constant, which is called E, is called eccentricity. And if you find the locus, so it is very clearly observed from here, this implies when E is constant, this is the form 1 over r is equal to 1 over d cos theta plus 1 over E d. So, this is the equation of a conic section. From here you can find out all these shapes like parabola, hyperbola, ellipse, etc., and of course, the circle. Now, let us compare the solutions. On my right panel, I have shown the equation of a conic section or the right. So, equation of a conic section, locus of a point which is whose ratio from the focus and directrix is a constant. So, that equation is shown on the right. This comes from geometry. On my left, I have written the solution of our differential equation, which comes from kinetics, and you can very easily see the similarity. With this redefinition, the d is 1 over c and eccentricity is c times h square by g m, and hence E d, the product of these two factors, which is E d, is h square by g m. So, with these definitions, they are the same. Therefore, the solution is a conic section. Now, what happens when E is equal to 0? So, C is equal to 0 implies E equal to 0. In that case, you will find that the radial coordinate essentially remains constant. It is no longer a function of theta. If radial coordinate is no longer a function of theta, it means that it is a circle, it is a circular path. Therefore, if E is 0, the eccentricity is 0, then C is 0, and hence your the locus is a circle. And you can find out the this radius of the circular locus. Radius of the circular locus can be found precisely from this equation by just putting c equal to 0, is h square by g m, and h, we know that its h is, we know that h is r c square theta dot, r c square theta dot, so the radius of the circle square into theta dot. Therefore, h square is r c to the power 4 theta dot square by g m. and this can be written because r c square theta dot square is this v c, the velocity on the circular path, which is actually v t, the tangential velocity. So, tangential velocity is r c into theta dot, and that is the orbital speed, the orbital speed of the particle called v c. So, the speed on the circular path is called orbital speed. Therefore, the orbital speed can be determined from this under root g m by r c. There is an alternate way of finding orbital speed. You can match the centripetal force with the gravitational force, and also from there also you can obtain the orbital speed. Now, orbital period, it is theta dot, is 2 pi by the time period is theta dot. Therefore, t square by r c cube is 4 pi square by g m. Now, this is a constant, this you can find out, right, this you can find out, and this is Kepler's third law, this is precisely Kepler's third law. So, just by substituting theta dot here, we can find out the orbital time period. So, orbital time period is this relates as 2 pi by theta dot. Orbital time period t, capital T is 2 pi by theta dot, and theta dot can be determined from all these expressions. So, to summarize, we started off with by discussing the Kepler's laws of planetary motion. Then we looked at Newton's law of gravitation and coupled it with the second law of Newton, and found out the governing differential equation, which we solved and found out that the solutions are nothing but conic sections. We have looked at only the first example of a conic section, which is a circle, the simplest of it, where eccentricity is 0, and basically these are this is the first step in study of central force motion. So, with that I will conclude this lecture.